The argument that we use to get line integrals for plane curves extends immediately to curves of 3 or more dimensions. So let f be continuous on a smooth curve C, and this curve R of t is given in terms of x, y, and z. The integral of the function on the curve C in 3 space will be the same formula. It's just a function evaluated at x, y, and z, where we're using the parameter t to represent the function, and then the magnitude of r prime of t. Now I want you to notice here that if we use the function, if the function f of x, y, z is just 1, so if this was just 1, this integral would just be the integral of r prime of t, its magnitude, which is just the integral of the square root of x prime squared plus y prime squared plus z prime squared, which is the formula that we had back in chapter 12 for arc length. Okay, so if the function f that we're trying to integrate is just 1, we're just calculating the arc length. Okay, so let's say also that the parameter t in this formula is s. So let's say that t is the arc length. Well, then that means that ds dt would just be 1, but that is the magnitude of r prime of t. So this will be 1 when t is the arc length. So then we're back to that original integral that we got first. So now this will be the formula that we use if we want to find scalar line integrals. Now that's where the function f is a scalar function. So you're integrating the function f, which gives you a real number, some value like a temperature. Okay, so now let's evaluate this function on this curve. So our first curve will be the line from the point 1, 0, 0 to 0, 1, 1. Now notice too that this integral that we're trying to evaluate is a function. This is a function of x, y, z. And if we plug in a point x, y, z, we get a real number. So this is a scalar function. Okay, so we want the line integral over the curve C, with respect to the arc length. So we can use any parameter though. So let's just find any parameterization for this line. We're looking for the line segment PQ. Okay, recall that when you wanted to find a line, using parametric equations, x was equal to x naught plus at, y was y naught plus bt, and z was z naught plus ct, where x naught, y naught, z naught was a point on the line, and the vector ABC was the direction vector, or a vector parallel to the line. Okay, so let's first find a vector parallel to this line PQ. So the vector V, I'll just call it V for the vector parallel. V would be the vector 0, minus 1. I'm just taking the point Q minus the point P. So 0 minus 1, 1 minus 0, and 1 minus 0. So that would be the vector negative 1, 1, 1. So that's a vector parallel to the line that we're trying to get a parameterization for. And now we're just going to pick any point. So let me just use this for my x naught, y naught, z naught. You can use either one of the 2 points. So the parameterization R, now the x will be x naught, which is 1. I'll just put them all down here. 1, 0, 0. There's your x naught, y naught, z naught, plus the vector is negative 1, 1, 1 times t. So your parameterization will be 1 minus t, 0 plus t, and 0 plus t. Okay, so that's your parameterization R of t. Well, that's the curve R of t, which is a parameterization for the curve, which is the line PQ. Okay, now what are the t values that represent the line? Now we're talking about just a line segment from P to Q, and so the parameter values that correspond to that, if we just use that vector that we get, not another multiple of it, the parameters t will go from 0 to 1. So now you can check it. If you put t equals 0, you will get the point x, y, z to be 1, 0, 0. And if you put in t equal 1, you will get that x is 0, y is 1, and z is 1. So the t values are from 0 to 1. Okay, so integrating over the curve will be the same thing as rewriting this function in terms of t. So we're going to have 1 minus t for the x, t for the y, plus 2 times the z, which is another t. And now we need to find the magnitude of the r prime of t, and then dt, and the t values are from 0 to 1. So let's find r prime. We had that r was 1 minus t, t, and t. So r prime would be negative 1, 1, 1. And so the magnitude of r prime would be the square root of negative 1 squared plus 1 squared plus 1 squared, which is the square root of 3. So this will be the integral. Let's see, this will be t minus t squared plus 2t, just distributing, times the square root of 3, which would be the same as the integral from 0 to 1 of negative t squared plus 3t. I'm going to put the square root of 3 out in front. Be minus t cubed over 3 plus 3t squared over 2, evaluated from 0 to 1. And then we put 0 in, everything's 0. Common denominator of 6. Seven times the square root of 3 over 6. So that's the value of that integral. So we're accumulating the function values over that curve. Okay, so now let's look at the line from Q to P. So we first need a parameterization. We're now starting at Q and ending at P. So x naught, y naught, z naught. We'll let be Q, which is 0, 1, 1. Our vector v that's parallel will be the vector QP, which will be 1 minus 0, 0 minus 1, 0 minus 1. Okay, and our parameterization then, the x, we'll go ahead and just put them in this notation right now. The x will be 0, the x naught 0, the y naught is 0, the z naught is 0. And now 1t minus 1t, I'm using the vector v for the ABC, minus t. And then again, the parameter values would be 0 to 1 to define the line segment from Q to P. And just check it. Putting in t equals 0, this becomes 0, 1, 1, which is Q. And if we put in t equal 1, this becomes 1, 0, 0, which is the point P. Okay, so now let's set up our integral. We're now integrating xy plus 2z over the curve C, which will be, we're plugging in t now for the x, 1 minus t for the y, and 1 minus t for the z. My r prime, okay, if r was t, negative t, oops, 1 minus t, 1 minus t, then r prime will be 1, negative 1, negative 1. So the magnitude of r prime will be, again, the square root of 3. So integrating minus t cubed over 3 minus t squared over 2 plus 2t. Put in 0 and everything 0. So we'll have, again, common denominator of 6. And again, we get 7 times the square root of 3 over 6. Now what this emphasizes is the path was the same path. The curve was the same. The only difference in these two parameterizations was the orientation, where we started, where we ended. So the orientation and the parameterization does not make any difference. So as long as the curve is the same and we're integrating the same scalar valued function, we should get the same answer. Okay, now let's look at one more example. An eagle soars on this ascending spiral path given by this parameterization. So x, y, and z are measured in feet. T is measured in minutes. We want to know how far the eagle flies. Okay, so the curve gives the path. So if we want to know the distance that it's traveled, then our function f that we're going to be integrating will just be 1. When you want the curve length, just use the function of 1. So the integral of f over the curve c becomes 1. Now, we still need the magnitude of r prime of t dt, changing the ds over. Okay, and since we're now going to use t, we're going to use from 0 to 10 for our parameter values, the limits of integration. So we've got our function r. So finding r prime, the derivative of cosine of 1/2 t will be 1/2 negative sine of t over 2. So we're going to have negative 1200 sine of t over 2. The derivative of sine of t over 2 will be 1/2 cosine of t over 2. So that'll be 1200 cosine t over 2. And then the derivative of 500t is just 500. So the magnitude of r prime of t will be negative 1200 squared sine squared of t over 2 plus 1200 squared cosine squared of t over 2 plus 500 squared. Now if you factor out the 1200 squared from the first two terms, you're going to have sine squared plus cosine squared, which is 1. So this will just be 1200 squared plus 500 squared, which actually comes out to be 1300 squared, because 5, 12, and 13 are a Pythagorean triple, which just gives us 1300. Okay, so our integral then becomes from 0 to 10, 1300 dt 1300 t evaluated from 0 to 10, which will be 13,000 minus 0. So 13,000 feet is the distance that the eagle will fly over that 10 seconds.